C-type asteroids. These are the most common asteroids in the solar system, making up the overwhelming majority of objects found in the outer regions of the asteroid belt. They are rich in carbon, which gives them a dark, almost charcoal-like appearance and a very low reflectivity, so dim that early astronomers sometimes struggled to detect them at all. Scientists believe these asteroids are some of the oldest, most unchanged material left over from the early solar system, essentially fossils from the cloud of gas and dust that once surrounded the young sun. Because they've barely changed in billions of years, they become valuable targets for missions studying the raw ingredients that eventually formed planets. And some researchers even think water on Earth may trace back to impacts from asteroids like these, S-type asteroids. Unlike their carbon-rich cousins, these asteroids are made mostly of silicate minerals mixed with nickel and iron, giving them a rocky, stony character. They tend to sit closer to the inner edge of the asteroid belt, where warmer conditions during the solar system's formation allow different materials to condense. Their surfaces are noticeably brighter and more reflective than C-type asteroids, which makes them easier to spot and track from Earth-based telescopes. Their composition closely resembles the materials thought to make up the interiors of rocky planets, so studying them helps researchers piece together how worlds like Earth and Mars might have formed from similar building blocks. M-type asteroids. These stand out because they contain a much higher concentration of metal, particularly nickel and iron, than most other asteroid types. Some researchers think they may be fragments of the metallic cores of much larger bodies that broke apart during violent collisions early in the solar system's history. If that theory holds, these asteroids could offer a rare glimpse into the interior of a planet-sized object without ever having to dig beneath a planet's surface. Because of this metal-rich makeup, they've drawn serious interest from private companies exploring the idea of asteroid mining, since a single one could theoretically contain more accessible metal than has ever been mined on Earth. Near-Earth asteroids. As the name suggests, these are asteroids whose orbits bring them into the vicinity of Earth's own path around the Sun. They vary widely in size, from small rocks just a few meters across to massive bodies several kilometers wide, and their numbers are much higher than most people realize, with tens of thousands already cataloged. Tracking these asteroids has become a major focus for space agencies, since their proximity means a small orbital shift over time could bring one uncomfortably close to our planet. Dedicated survey programs now scan the sky nightly, hunting for new discoveries and refining the orbits of ones already known. Main belt asteroids. Most asteroids in the solar system live here, in the wide region between the orbits of Mars and Jupiter. This belt contains millions of individual objects, ranging from tiny fragments barely visible to bodies hundreds of kilometers across, with the largest Ceres massive enough to be classified as a dwarf planet. Despite popular imagination, the objects here are spread out over such a vast area of space that spacecraft can pass through the belt without much real risk of collision. Gravitational interactions with Jupiter have carved out gaps within the belt over time, sorting asteroids into distinct bands and occasionally flinging some out toward the inner solar system. Trojan asteroids. These asteroids share an orbit with a planet, clustering at two stable points located ahead of and behind it along its path around the Sun. Jupiter has by far the largest known population of these companions, with thousands identified so far, though other planets, including Earth and Neptune, have been found to have a few of their own. Their unusual positioning is the result of a gravitational balance point, where the combined pull of the planet and the Sun creates a stable pocket that traps objects in place for millions of years. Spacecraft have recently been sent to study Jupiter's Trojans up close, hoping to learn whether they formed alongside the giant planet or were captured from elsewhere. Centaur asteroids. These occupy a strange middle ground between asteroids and comets, orbiting in the outer solar system somewhere between Jupiter and Neptune. Their icy composition means they sometimes develop faint comet-like tails when warmed slightly by sunlight, blurring the usual distinction between the two types of objects. Because their orbits cross the paths of giant planets, they experience frequent gravitational nudges that make their paths unstable over long timescales. Many are thought to eventually get flung either closer to the sun, where they may become active comets, or out toward the frozen edges of the solar system, never to be seen again. Binary asteroids. Some asteroids don't travel alone, but instead orbit a companion, forming a pair that circles a shared center of gravity as they move through space together. These systems can form when a larger asteroid gets struck hard enough to split apart, sending debris into orbit around the remaining body, or when close gravitational encounters cause one object to capture another passing by. Roughly 1 in every 6 near-Earth asteroids is now believed to have a companion of some kind. Studying these pairs gives scientists a rare opportunity to measure an asteroid's mass directly by observing how strongly it pulls on its partner, something that's normally very difficult to determine from a single object alone. Rubble pile asteroids. Rather than being solid rock, these asteroids are loosely bound clusters of debris held together mainly by their own weak gravity, rather than any real structural strength. This makes them surprisingly fragile, despite their often impressive size, and it also means they respond to impacts very differently than a solid object would, absorbing and dispersing energy rather than shattering cleanly. Missions that have visited these asteroids up close have found their surfaces covered in loose boulders, shifting gravel, and fine dust that behaves almost like a fluid in low gravity. This porous, crumbly nature has become an important factor in planning any future mission that might try to redirect one. Monolithic asteroids. In contrast to rubble piles, these are single, solid chunks of rock or metal without the loose, fragmented structure seen elsewhere in the asteroid population. They tend to be denser and far more resistant to breaking apart under stress, whether from a passing gravitational tug or a collision with a smaller object. Their solid, uniform nature also makes them easier to model mathematically, since engineers can predict how they behave if ever struck or nudged off course with much greater confidence. Some scientists suspect that certain smaller asteroids may actually be monolithic fragments broken off from larger rubble pile parents, potentially hazardous asteroids. This classification is given to asteroids that come close enough to Earth's orbit and are large enough that a future impact, however unlikely, could cause significant regional or even global damage. Astronomers monitor these objects carefully, using repeated observations to calculate their paths years or even decades into the future with remarkable precision. Being labeled this way doesn't mean a collision is expected anytime soon, only that the object's size and orbit warrant close, ongoing attention from tracking programs around the world. Several international efforts now exist specifically to catalog and refine the orbits of every asteroid that falls into this category. Apollo asteroids. These near-Earth asteroids follow orbits that cross Earth's own path around the Sun, spending part of their time closer to the Sun than we are and part of it farther out beyond our orbit. Named after the first asteroid discovered with this particular orbital pattern back in the 1930s, they represent one of the more closely watched groups due to how frequently their paths intersect our own. Many of the asteroids considered potentially hazardous fall into this category, simply because crossing Earth's orbit repeatedly increases the long-term odds of a close approach. Some Apollo asteroids have orbital periods similar to Earth's own year, meaning they return to our neighborhood again and again on a predictable, recurring schedule. A10 asteroids. These near-Earth objects are defined by having orbits smaller than Earth's, spending most of their time closer to the Sun and only occasionally swinging out far enough to cross our planet's path. Because their orbits keep them mostly on the sunward side, they can be genuinely difficult to detect using ground-based telescopes, which mainly search the night sky away from the sun's glare. This observational blind spot means a meaningful number of A10 asteroids likely remain undiscovered even today. Specialized space-based telescopes positioned to look sunward have become one of the more promising tools